Ever struggled with solving tricky differential equations where step size is too small or too large? Today we'll explore the adaptive Runge-Kutta method, which intelligently adjusts step size to handle even stiff equations that can trip a standard fourth-order Runge-Kutta method. Let's dive in and see it in action. The method that we will see is known as Runge-Kutta-Fehlberg method, or also known as RK45. This is an embedded method. At each step, we calculate two solutions using different order RK methods, one using fourth order accuracy and another with fifth order accuracy. We then compare these two solutions to estimate the local truncation error. If the error is too large, we reduce the step size, or if it is too small, we increase the step size. This makes the method both reliable and efficient. We can start with the generalized integration formula, where the increment function phi is weighted sum of the stage derivatives or intermediate slopes that is represented by k. The corresponding Butcher tableau shows the value of p, q, and a for each stage used in this method. For the values of a, we have two rows. The top row shows the values for fourth order accuracy, whereas the bottom row shows the values for fifth order accuracy. We can then estimate the local truncation error using these two solutions, and if the error is below a threshold, we update the solution. Otherwise, we will repeat the same step with different step size. That is obtained by multiplying the current step size with this delta value. The solution for the same differential equations with RK45 is much more accurate. We started with h is equal to 1 and the method itself changed the step size, especially where the function changes were rapid. The step size in this area became smaller. However, in other areas, the method uses larger step size, thus making it both reliable and efficient. This concludes the video. I hope you liked it. Don't forget to subscribe to my channel. Thanks for tuning in and see you in the next one.